Welcome back to Naptime Knowledge. Take a breath. Let it be slow and full and easy, the way breath comes when the body is truly at rest. Let your shoulders drop. Let your hands open. Let the weight of everything you have been carrying today, the decisions, the worries, the noise, let all of it settle gently downward, like sand drifting through still water, finding its level, coming to rest. Tonight's journey is different from the ones we have taken before. We are not going to a specific civilization or a historical period or a named mystery. We are going somewhere older than all of those things. We are going to the ocean. The ocean is the oldest thing on Earth that is still itself. The mountains have been worn down and rebuilt. The continents have moved. The atmosphere has changed its composition several times. Even the land itself has been recycled through the interior of the planet and brought back to the surface in new forms. But the ocean has been here, covering most of the planet's surface for more than 4 billion years. It was here before life. It was the birthplace of life. It has witnessed every era of Earth's history, absorbed every catastrophe, and remained, through all of it, essentially itself. Vast, deep, salt, dark, alive. There is something about the ocean that reaches past the thinking mind and speaks directly to something older and quieter in us. Something pre-verbal, pre-rational, something that remembers, without knowing it remembers, that we came from the sea. The first creatures to breathe air and walk on land carried the ocean with them in their blood, in the salt concentration of their body fluids, in the rhythms of their breathing, in the deep chemical familiarity of salt water and living tissue. We are creatures of the land who have never quite forgotten the sea. Tonight we are going to remember it. We are going to move through the ocean slowly, from the surface to the deep, from the tropics to the poles, from the present to the deep past. And in moving through it, we are going to find, I hope, the particular quality of peace that only very large and very old things can give. The ocean does not hurry. The ocean does not worry. The ocean simply is, enormous and patient and indifferent and alive. And in its presence, the small urgencies of a single human day become very quiet indeed. Breathe. Settle. The tide is coming in. Before we begin, find a comfortable position. Let your body settle. Feel the weight of your limbs. Feel the surface beneath you, holding you completely. Gently close your eyes, or let your gaze go soft. We are going to breathe together for just a few moments, slowly, deeply, and with each breath, you will feel yourself becoming a little more relaxed, a little heavier, a little more ready for rest. Take your first breath in, slowly. Feel your chest and belly rise. Breathe in. 2, 3, 4. Hold. 2, 3, 4. Release. 2, 3, 4. Good. Let your shoulders drop. Let your jaw unclench. Let your hands go soft. Breathe in. 2, 3, 4. Hold. 2, 3, 4. Release. 2, 3, 4. With this breath, Let go of the day. Whatever happened today, whatever you carried, whatever you managed, whatever you left unfinished, you can set it down now. It will be there if you need it tomorrow. Tonight, it can rest. Breathe in. 2, 3, 4. Hold. 2, 3, 4. Release. 2, 3, 4. Notice how heavy your body feels. Notice how quiet the room is. Notice how the breath moves through you like a slow, dark tide. In and out, unhurried and easy. You do not need to do anything right now. You do not need to be anywhere. You do not need to solve anything, or remember anything, or prepare for anything. The only thing that exists right now is this breath, and this quiet, and the story that is about to begin. Breathe in. 2, 3, 4. Hold. 2, 3, 4. Release. 2, 3, 4. When you are ready, let your breathing return to its own natural rhythm. Let it be effortless, and as you breathe, let the words of the story carry you slowly, gently, down towards sleep. Chapter 1. The Surface. Where the ocean meets the sky. Begin at the surface. Not the churning surface of a storm, not the cold grey surface of a northern winter, but the surface on a calm day, in a warm latitude, when the sea is at rest and the light is doing extraordinary things with the water. On a clear, still day in the open ocean, far from any shore, the surface of the sea has a quality of light that is unlike anything on land. The water is not simply blue. It is a blue that changes with every shift of angle and depth and weather, moving through shades that have no exact names. The pale, almost white blue of shallow tropical water over sand. The deep, saturated blue of the open Atlantic, called navy by the color charts, but actually closer to the blue of a twilight sky. The greenish blue of colder northern waters, where different populations of phytoplankton tint the water with their collective presence. The extraordinary cobalt of the Mediterranean on a summer afternoon, so intensely colored that it seems almost artificial. The surface of the ocean is not flat. Even on the calmest days it moves, long, slow swells that have traveled hundreds or thousands of miles from wherever a storm stirred them into existence. These swells are the ocean's memory of distant weather, waves that have been running across the open sea for days or weeks, their energy declining slowly as they travel, arriving finally at a far shore as the gentle, rolling surf that makes beaches such peaceful places. The ocean communicates with itself across vast distances through these swells, sending messages of wind and storm from one side of the basin to the other. At the surface, the ocean and the atmosphere are in constant conversation. The sea breathes, absorbing carbon dioxide from the air, releasing oxygen, exchanging heat and moisture with the atmosphere above it. The great currents of the ocean are driven partly by this exchange, by differences in temperature and salinity that make some water denser than others, causing it to sink and creating the slow conveyor belt of deep ocean circulation that distributes heat around the planet. Without the ocean, Earth's climate would be unrecognizable. The continents would be far more extreme in their temperatures. the distribution of rainfall would be completely different, and life as we know it would not exist in its current form. The surface is also where the ocean's most famous residents live, the great whales, humpback whales, blue whales, sperm whales, right whales. These extraordinary animals spend their lives in intimate relationship with the surface, rising to breathe every few minutes, breaching in great arching leaps that seem impossible for animals of their size, slapping the water with their flukes in behavior that scientists believe serves social functions. The blue whale is the largest animal that has ever lived on Earth, larger than any dinosaur, larger than anything the fossil record shows. A blue whale's heart is the size of a small car. Its heartbeat can be heard from 2 miles away through specialized hydrophones. It produces sounds that travel thousands of miles through the ocean, communicating with other blue whales across an entire ocean basin. The sounds of the ocean are a world in themselves. The surface is alive with sound. The slap and hiss of waves, the click of shrimp in the shallows, the song of whales in the open water, the distant rumble of underwater earthquakes. The ocean conducts sound more efficiently than air, and sounds travel farther and faster in water than they do above the surface. Scientists have discovered that the ocean has a natural acoustic channel, a layer of water at a specific depth where sound waves are trapped and can travel enormous distances with minimal loss. Blue whales use this channel to communicate. Submarines use it for navigation. And it means that the ocean is full of sound that we cannot hear unless we put our ears or our hydrophones below the surface. Lie very still. Imagine the surface of the ocean on a calm day. The long, slow movement of the swells, the light moving on the water, the horizon curving away in every direction. You are very small in relation to this. The ocean does not notice you, and somehow that is the most peaceful thought of all, to be held by something so large that your smallness is simply a given, unremarkable, comfortable. Breathe in. 2, 3, 4. Hold. 2, 3, 4. Release. 2, 3, 4. Chapter 2. The Shallows. Reefs, kelp forests, and the sunlit zone. Move inward from the open ocean toward the places where the sea floor rises and the water becomes shallow and light can reach the bottom. These are the richest, most productive, most extraordinarily diverse environments in the ocean. The coral reefs and kelp forests and seagrass meadows that are home to a disproportionate share of all the species that live in the sea. Coral reefs are built by tiny animals, coral polyps, that secrete calcium carbonate skeletons and live in colonies of millions or billions of individuals. Over years and decades and centuries, these skeletons accumulate into the complex, branching, three-dimensional structures that form the physical basis of the reef. The Great Barrier Reef of Australia, the largest living structure on Earth, visible from space, is the accumulated effort of billions of coral polyps over tens of thousands of years. A structure roughly the size of Italy, built by animals smaller than a fingernail. Inside a coral reef, the density of life is staggering. Fish of extraordinary variety and color dart between the coral branches. The blue and yellow of a parrotfish, the electric blue of a damselfish, the improbable orange and white of a clownfish sheltering among the stinging tentacles of an anemone. Octopuses move through the gaps in the coral, changing color and texture as they go, disappearing and reappearing in a way that seems like magic. Sea turtles glide through with unhurried elegance, ancient and serene, their bodies unchanged in their essential form for millions of years. Reef sharks patrol the deeper channels with quiet menace. Giant clams sit on the reef floor, their mantles patterned in blues and greens and purples that have no clear evolutionary explanation. They are simply beautiful, for reasons that life seems sometimes to produce without any particular survival advantage. The relationship between coral polyps and the microscopic algae that live inside their tissues, the zooxanthellae, is one of the most important partnerships in the living world. The algae photosynthesize, using the energy of sunlight to produce sugars that the coral polyp uses for food. In return, the coral provides the algae with shelter and the minerals they need to grow. The relationship is so intimate and so essential that when the water warms too much, as it does during marine heat waves that are becoming more frequent with climate change, the coral expels the algae in a process called bleaching, turning white. Without the algae, the coral is stressed and eventually dies, leaving behind a skeleton of bare calcium carbonate, ghostly and silent, where there was once noise and color and life. Kelp forests are the ocean's version of the great terrestrial forests, towering, three-dimensional structures of living organisms that create habitat for hundreds of other species. Giant kelp, which grows in cold, nutrient-rich coastal waters, can reach 30 meters in height, taller than a 10-story building, and can grow as fast as 60 centimeters per day, making it one of the fastest-growing organisms on Earth. A kelp forest seen from inside, looking upward through the green columns of the stipes toward the canopy, where the fronds spread out to capture the light, has a quality of underwater cathedral, an architecture of living things, solemn and beautiful and full of slow movement. Sea otters are the keystone species of the kelp forest, the animal whose presence is most critical to the health of the entire ecosystem. Sea otters eat sea urchins, which in turn eat kelp. Without otters, sea urchin populations explode and devour the kelp forest, turning a complex, three-dimensional habitat into a flat, barren seafloor called an urchin barren. With otters present, the urchins are kept in check, the kelp forest thrives, and the entire community of species that depends on it, the fish and the invertebrates, and the marine mammals and the seabirds, flourishes. The sea otter is a small animal, charming and playful, famous for sleeping, wrapped in kelp to keep from drifting away. And it holds together one of the most complex ecosystems on Earth, simply by eating its lunch. The sunlit zone of the ocean, the uppermost 200 meters where light penetrates sufficiently for photosynthesis, is where almost all of the ocean's primary productivity occurs. Phytoplankton, microscopic, single-celled algae, float in their billions throughout these waters, photosynthesizing sunlight and carbon dioxide into organic matter that forms the base of the entire marine food web. Phytoplankton are responsible for roughly half of all the oxygen produced on Earth. Every other breath you take comes from the sea, from these invisible, enormously productive organisms that have been doing their quiet work for billions of years. The beauty of the sunlit ocean is inseparable from its productivity. The colors, the clarity, the extraordinary variety of living forms, all of it is a consequence of the energy pouring down from the sun and being captured and transformed and passed up through the food web, from phytoplankton to zooplankton, to small fish to large fish, to the great predators at the top, in a web of energy transfer so complex that scientists have barely begun to map it. Let the image of that sunlit water fill your mind, the shafts of light descending through the blue, the reef below alive with color and movement, the slow undulation of the kelp forest, the sea otter on its back on the surface, cracking an urchin on the flat stone it carries on its chest, perfectly at home in a world that was old before any human being ever saw it. Chapter 3. The open ocean, vast, blue, and alive. Move away from the shallows, away from the reefs and the kelp forests, out into the open ocean. The water deepens, the bottom disappears. The blue around you becomes deeper, more saturated, more absolute. You are in the pelagic zone, the open water column, hundreds or thousands of meters deep, stretching away in every direction to the horizon. The open ocean covers more than half the surface of the Earth. It is, by area, the largest habitat on the planet, and it is one of the least understood. The animals that live in the open ocean are difficult to study because there are no fixed structures to return to, no reefs or rocky outcrops to anchor a research station. The animals themselves are often at depth, or move constantly, or are simply too small and too dispersed to study easily. Our knowledge of open ocean ecology is fragmentary and incomplete, and new discoveries are made on almost every research expedition. The animals of the open ocean are extraordinary in their adaptations to an environment that offers almost nowhere to hide, almost nothing to hold on to, and almost no landmarks of any kind. Tuna are among the most perfectly adapted, streamlined to the point of abstraction, their bodies shaped by millions of years of selection for speed and efficiency. A bluefin tuna can swim at speeds exceeding 70 kilometers per hour, sustain high speeds for long distances, and cross the entire Pacific Ocean in a matter of weeks. They are endothermic, warm-blooded, in the way that mammals are warm-blooded, capable of maintaining their body temperature above the ambient water temperature, which gives their muscles a performance advantage that cold-blooded fish cannot match. Manta rays drift through the open water with a slow, wing-like grace that seems effortless but covers enormous distances. Their wingspan can reach 7 meters. They feed on zooplankton, tiny crustaceans and fish larvae, filtering them from the water as they swim with mouths agape, the water passing over their gill plates and the plankton being retained. They are gentle, curious, and apparently highly intelligent. They have been observed approaching divers with what seems like curiosity, circling and watching, showing none of the wariness that most large marine animals display toward humans. The open ocean at night is a different world from the open ocean in daylight. After dark, the deep-sea animals that spend the day in the darkness below begin their nightly migration toward the surface. The diel vertical migration, one of the largest animal movements on Earth, occurring every night in every ocean, as billions of creatures rise from the deep to feed on the plankton-rich surface waters and then descend again before dawn. The scale of this movement is almost incomprehensible. An estimated 10 billion tons of marine organisms, fish and squid and crustaceans and jellyfish, move vertically through the water column every single night. In doing so, they transport enormous quantities of carbon from the surface to the deep ocean, playing a crucial role in the global carbon cycle. The bioluminescence of the open ocean is one of its most magical features. Many open ocean organisms, fish, squid, jellyfish, dinoflagellates, produce their own light through chemical reactions in specialized organs. In the surface waters at night, a ship moving through the ocean can produce a wake of glowing blue-green light as the bow wave disturbs the bioluminescent dinoflagellates, which flash in response to mechanical disturbance. Swimming through such water is an experience that those who have had it describe as otherworldly. The body trailing light through the darkness, every movement sparking brief galaxies of cold blue fire. Sperm whales hunt in the deep ocean, diving to depths of more than a kilometer in pursuit of giant squid and other deep-sea prey. They are the largest toothed predators on Earth. Males can reach 18 meters in length. They navigate by echolocation, sending powerful clicks through the water and reading the echoes to construct a three-dimensional acoustic image of their environment. The clicks of a sperm whale are the loudest sound produced by any animal. They can reach 230 decibels, enough to stun prey at close range. In the dark, in the deep, the sperm whale is the apex predator of an ecosystem that most of us will never see. The open ocean is vast enough to make human activity seem trivial, and yet it is not immune to human influence. Plastic pollution has distributed synthetic particles throughout the world's oceans, from the surface to the deepest trenches. Overfishing has depleted populations of large predators that took millions of years to evolve. Climate change is altering the temperature and chemistry of the ocean in ways that cascade through the entire ecosystem. The ocean absorbs roughly a quarter of all the carbon dioxide that human activity releases into the atmosphere. And as the dissolved carbon dioxide reacts with water to form carbonic acid, the ocean is becoming more acidic, a process that threatens the ability of coral and shellfish and many other organisms to build their calcium carbonate shells and skeletons. And yet the ocean endures. It has survived 5 mass extinctions. It has survived the asteroid impact that killed the dinosaurs, the ice ages that locked up enormous quantities of water in glaciers, the volcanic episodes that poisoned the atmosphere with sulfur dioxide. It will almost certainly survive us, in some form, however altered. The ocean is older than all the challenges it has faced. It does not panic. It does not despair. It absorbs what it absorbs and continues, vast and patient, doing what it has always done. Breathe. Let the open ocean settle around you like darkness around a small light. You are warm and safe on the surface, or close to it, held up by the extraordinary buoyancy of salt water, which is denser than fresh water and more willing to keep you afloat. The stars are coming out above you. The ocean is very dark below, and in between, in the thin membrane of the surface, life is happening. in its millions of forms, beautiful and indifferent, and endlessly various. Chapter 4. The Deep Ocean. Dark, cold, and strange. Now we descend. Below the sunlit zone, below the twilight zone, where the last traces of light fade to nothing, into the deep ocean, the bathypelagic zone, the abyssal zone, the hadal zone of the deep trenches. We are going to the part of the ocean that is most alien, most extreme, and most full of creatures that seem to belong to a different world entirely. The light disappears quickly. Below about 200 meters, there is not enough sunlight for photosynthesis. Below 1,000 meters, there is essentially no sunlight at all. Below 2,000 meters, the darkness is absolute and permanent. It has never been touched by natural light in any form since the ocean formed 4 billion years ago. This is a darkness that is not simply the absence of light. It is a positive quality, a feature of the environment as real and as significant as temperature or pressure. The animals of the deep ocean have evolved in this darkness for hundreds of millions of years, and they have developed ways of living in it that are unlike anything in the sunlit world above. The pressure in the deep ocean is one of its most extreme features. At the surface, the pressure is 1 atmosphere, the weight of the air column above you. At 1,000 meters, it is 100 atmospheres. At the bottom of the Mariana Trench, the deepest point in the ocean at nearly 11 kilometers, the pressure is more than 1,000 atmospheres, enough to crush a conventional submarine, enough to compress water itself measurably. The animals that live at these depths have evolved biochemistry specifically adapted to high pressure. Their cell membranes contain lipids that remain fluid under conditions that would make the lipids of surface animals solid. Their proteins fold and function correctly at pressures that would denature the proteins of surface animals. The temperature in the deep ocean is uniformly cold, close to freezing throughout most of the abyss. This cold is a consequence of the deep ocean circulation. The water at the bottom of the ocean sank from the surface in the polar regions, where it was cooled and made dense by cold temperatures and high salinity, and it has been slowly circulating at depth ever since, carrying its polar cold with it. The deep ocean is a reservoir of cold that helps to moderate the climate of the planet, absorbing heat slowly and releasing it slowly, acting as a thermal buffer against rapid climate change. In the dark and the cold and the pressure, life finds ways. The anglerfish is perhaps the most famous of the deep-sea creatures, a fish with a bioluminescent lure dangling from a modified fin spine on its head, used to attract prey in the darkness. The light is produced by symbiotic bacteria living in the lure, not by the fish itself. Female anglerfish can be considerably larger than males, and in some species, the males have evolved into little more than reproductive parasites, attaching themselves permanently to the female's body and fusing with her circulatory system, their organs degenerating until all that remains is a small packet of sperm, nourished by the female's blood and ready when she needs them. The viperfish, which lives at the mesopelagic zone at intermediate depths, has teeth so large relative to its body size that it cannot close its mouth. The teeth are designed to impale prey on a single strike in the darkness, preventing escape. The gulper eel has a jaw that can open wide enough to swallow prey larger than its own body, an adaptation for an environment where meals are rare and must be maximized. The giant squid, which can reach lengths of 12 to 14 meters, remains one of the least understood animals on Earth. Living at depths where it has rarely been observed alive, its biology inferred largely from stomach contents of sperm whales and the occasional specimen that washes ashore. The hydrothermal vents are perhaps the most extraordinary environments in the deep ocean. These are fissures in the ocean floor where superheated, mineral-rich water emerges from the Earth's crust, heated not by the sun, but by the heat of the Earth's interior. The water emerging from black smoke vents can reach temperatures of more than 400 degrees Celsius, kept liquid by the enormous pressure. Around these vents, in conditions that would be immediately lethal to almost all surface life, thriving communities of organisms have developed. Tube worms up to 2 meters long, giant clams, dense populations of shrimp and crabs, all sustained not by photosynthesis, but by chemosynthesis, the metabolic conversion of the chemicals emerging from the vents into organic matter. The discovery of hydrothermal vent ecosystems in 1977 by researchers aboard the research submersible Alvin was one of the most significant biological discoveries of the 20th century. It demonstrated that life did not require sunlight, that an entire complex ecosystem could be sustained by chemical energy alone in complete darkness at temperatures and pressures that seemed absolutely hostile to life. This discovery transformed our understanding of the limits of life on Earth and opened up the possibility that life might exist in similar environments elsewhere in the solar system, in the subsurface oceans of Jupiter's moon Europa or Saturn's moon Enceladus, where hydrothermal activity might provide the energy for life in the dark beneath kilometers of ice. The deep ocean floor is not featureless. It has mountain ranges, the mid-ocean ridges, where new seafloor is being created by volcanic activity, that are the longest mountain ranges on Earth, stretching for more than 60,000 kilometers through every ocean basin. It has volcanoes and plateaus and abyssal plains as flat as anything on Earth's surface. It has the deep trenches, where one tectonic plate slides beneath another and is consumed back into the mantle. And it has, scattered across its surface, a remarkable diversity of sediments and minerals and biological features that scientists are only beginning to map. Descend slowly in your imagination. Feel the pressure increasing, the temperature dropping, the light fading to nothing. The water around you is very dark, very cold, very still. Something bioluminescent flashes briefly in the distance, a pulse of blue-green light, quick as a thought, and then dark again. You are very deep. You are very safe. And the darkness is not threatening. It is simply what darkness is when it has had 4 billion years to become completely itself. Chapter 5. The Ocean. Through time, 4 billion years of history. The ocean we know today, with its coral reefs and its whales and its phytoplankton and its deep-sea fish, is the product of 4 billion years of evolution and change. The history of the ocean is the history of life itself, and it is one of the most extraordinary stories that can be told. When the Earth formed, approximately 4.5 billion years ago, there was no ocean. The young planet was hot, still warm from the energy of its formation and from the continuous bombardment of asteroids and comets that characterized the first 500 million years of solar system history. The surface was molten or nearly so, and any water that arrived in the early period was immediately vaporized into a hot, dense atmosphere of steam and carbon dioxide and nitrogen. The water that eventually formed the ocean came, in significant part, from space. Comets and water-rich asteroids that bombarded the early Earth delivered hydrogen and oxygen that eventually became water. As the planet cooled and the bombardment slowed, this water condensed into the first oceans, still hot, still under a thick and hostile atmosphere, but liquid and present. By roughly 4 billion years ago, the ocean existed in something like its current form, covering most of the planet's surface, connecting the scattered land masses, beginning the great work of chemistry that would eventually produce life. The first life on Earth almost certainly appeared in the ocean, and almost certainly appeared near hydrothermal vents, or in tidal pools, or in some other chemically active environment where the ingredients of life could be concentrated and energized. The exact nature of the first living things is unknown and perhaps unknowable. They left no fossils, and we can only infer their nature from the biochemistry shared by all living things today. What we know is that by approximately 3.5 billion years ago, life was present on Earth. Simple, single-celled organisms, probably something like modern bacteria, living in the ocean and beginning the long, patient process of evolving into everything else. For the first 2 billion years of life's history, more than half of life's entire existence on Earth, it remained single-celled and microbial. The ocean during this long period was not the clear, blue, oxygen-rich environment we know today. It was a very different place, warmer, with a different chemistry, its atmosphere dominated by nitrogen and carbon dioxide and methane rather than oxygen. The organisms that lived in it were the ancestors of modern bacteria and archaea. Simple, but not simple in their biochemistry, which was already extraordinarily sophisticated. The Great Transformation came with the evolution of photosynthesis, specifically the evolution of oxygenic photosynthesis, the ability to split water molecules using sunlight and release oxygen as a byproduct. This appears to have evolved in the ancestors of modern cyanobacteria, sometime around 2.5 to 3 billion years ago, and it transformed the planet completely. As cyanobacteria multiplied and photosynthesized, they released oxygen into the atmosphere, oxygen that had previously been almost entirely absent. Over hundreds of millions of years, the Great Oxidation Event gradually changed the Earth's atmosphere from anoxic to oxic, from one with almost no free oxygen to one with the roughly 20% oxygen we breathe today. This transformation was catastrophic for the anaerobic organisms that had dominated the planet, organisms that could not tolerate oxygen and that were poisoned by its accumulation. But it was the enabling event for the evolution of all complex, multicellular life. Oxygen-powered metabolism is far more efficient than the anaerobic alternatives, allowing organisms to extract much more energy from the food they eat. Complex, multicellular organisms, with their requirement for high levels of sustained energy production, could not have evolved without oxygen. The Cambrian explosion, roughly 540 million years ago, was the moment when complex animal life suddenly diversified into an extraordinary range of forms. In a geologically brief period, roughly 20 million years, the major body plans of all modern animal groups appeared in the fossil record, along with dozens of body plans that have since gone extinct. The ocean at this time was an extraordinary place, alive with creatures that seem alien to our eyes. Experiments in body plan and lifestyle that have left no modern descendants. Since the Cambrian, the ocean has seen 5 mass extinctions, events of catastrophic biodiversity loss that wiped out large percentages of all marine species and reset the evolutionary trajectory of life in the sea. The most devastating was the end Permian extinction, approximately 252 million years ago, which killed roughly 96% of all marine species. It was followed by a long, slow recovery over tens of millions of years, during which the ocean's ecosystems were rebuilt from the survivors. The end Cretaceous extinction, 66 million years ago, caused by the asteroid impact that killed the non-avian dinosaurs, was less severe in the ocean than on land, but it still eliminated large numbers of marine species and cleared the way for the radiation of modern marine mammals, including the ancestors of the whales. The ocean we swim in today is the product of all of this history. Every mass extinction survived, every recovery completed, every evolutionary experiment tried and either succeeded or failed. It is the latest version of something 4 billion years old, continuously reinventing itself, continuously producing new forms from old materials, continuously finding new ways to be alive in the conditions that the planet provides. It is, in this sense, the most resilient thing on Earth and the most ancient. And lying here in the dark, knowing that the ocean is out there, doing what it has always done, there is something profoundly peaceful about it. Chapter 6. Tides. The moon's long conversation with the sea. Of all the forces that shape the ocean, none is more ancient or more poetic than the tide. The tide is the ocean's response to the gravity of the moon, a response so faithful and regular that human beings figured out how to predict it thousands of years before they understood the physics behind it. The tide is the ocean breathing in slow motion, drawn in by the moon's pull and releasing again as the earth rotates beneath it, in a rhythm so reliable that entire civilizations have organized their fishing and their trading and their lives around it. The basic mechanics of the tide are straightforward once you have Newton's law of gravitation to work with. The moon's gravity pulls on everything on Earth, but because gravity decreases with distance, the pull is strongest on the side of the Earth closest to the moon and weakest on the side farthest away. The water on the near side is pulled toward the moon, creating a bulge. The water on the far side is pulled less strongly than the solid Earth beneath it, effectively creating a bulge on the far side too. As the Earth rotates beneath these two bulges, any given point on the ocean's surface experiences 2 high tides and 2 low tides per day, though the exact pattern depends on the local geography. The sun also contributes to the tide, though its tidal effect is weaker than the moon's, because although the sun is vastly more massive, it is also vastly more distant. When the sun and moon are aligned, at new moon and full moon, their tidal effects add together, producing the large spring tides. When the sun and moon are at right angles, at the quarter moons, their effects partially cancel, producing the smaller neap tides. This pattern repeats every lunar cycle, with a reliability that ancient mariners could observe and predict long before anyone understood why it happened. The tidal range, the difference between high tide and low tide, varies enormously from place to place, depending on the shape of the ocean basin and the coastline. In the open ocean, tidal range is small, typically less than a meter. In enclosed bays and estuaries, the tidal wave can be amplified dramatically. The Bay of Fundy, between Nova Scotia and New Brunswick in Canada, has the largest tidal range in the world, more than 16 meters between low and high tide. Twice a day, an enormous volume of water rushes into the bay on the incoming tide and then rushes out again, carving channels and exposing vast mudflats that are rich in invertebrate life and feeding grounds for enormous numbers of shorebirds. The tidal zone, the region of coastline between the highest and lowest tidal marks, is one of the most challenging environments on Earth for the organisms that live in it. They are alternately submerged in seawater and exposed to the air, subject to extremes of temperature and desiccation and wave action that would kill most marine organisms in a matter of hours. And yet the intertidal zone is extraordinarily diverse and productive, one of the most species-rich habitats in the marine environment, inhabited by organisms of extraordinary toughness and ingenuity. Limpets clamp themselves to rocks with a muscular foot that can exert a force of 60 kilograms per square centimeter, enough to hold them in place against the most powerful waves. Mussels filter feed during the submerged periods and close their shells tightly during exposure, surviving hours of air exposure by drawing on the small reserve of water retained inside the shell. Sea stars hunt mussels and barnacles and other intertidal prey, moving slowly across the rock surface on hundreds of tiny tube feet. Crabs scuttle into crevices as the tide recedes, waiting in the dampness for the water to return. The intertidal zone changes visibly over the course of a tidal cycle. At high tide, the rocks are submerged and alive with movement. The water is full of plankton, and the rock surfaces are covered with filtering organisms, making the most of the incoming food supply. At low tide, the rocks are exposed, and the zone looks almost static. The limpets and barnacles and mussels closed against the air, the pools of water left in depressions filled with trapped animals waiting for the sea to return. And then the tide turns. The water advances up the beach grain by grain, and the zone comes alive again. The tide has marked time for human beings since before recorded history. Fishermen have always known that certain fish can only be caught on certain states of the tide. Sailors have always known that certain harbors can only be entered or exited at high water. The great tidal mills of medieval Europe mills powered by the incoming and outgoing tide rather than by river current, are monuments to the human capacity to harness the ocean's rhythms for productive work. And the tide tables that mariners have consulted for centuries, those extraordinary documents predicting the height of the tide at specific locations for years in advance, are among the most useful applications of applied mathematics that the ancient and medieval world produced. The tide is the most reliable thing in the ocean. It has been running for as long as the moon has been in orbit, roughly 4.5 billion years, though the early tides were much more powerful. Because the moon was closer to the Earth and its gravitational pull was stronger, the moon is slowly moving away from the Earth, a few centimeters per year, and the tides are slowly becoming less powerful as it does. In billions of years, the moon will be distant enough that the tidal effect on Earth will be negligible. But not tonight. Tonight, the tide is doing what it has always done, with the patience and the regularity of physics, rising and falling, as faithful as the moon itself. The tide is coming in somewhere right now. Feel it. The water advancing up the beach in long, slow rushes, each one reaching a little farther than the last. The foam hissing over the sand, the weight of the ocean pressing forward with the slow, irresistible authority of gravity and the moon. Then the retreat, the water pulling back, the sand gleaming, the temporary quiet before the next wave arrives. In and out, as regular as breathing, as old as the moon. Chapter 7. Ocean Currents, the Rivers of the Sea. The ocean is not a static body of water. It is in constant motion, not just at the surface, where winds drive waves and swells, but throughout its entire depth, in the slow and complex circulation of the great ocean currents that distribute heat and nutrients and living organisms around the planet. Understanding the ocean currents is understanding one of the most important systems in Earth's climate, and one of the most beautiful. The surface currents of the ocean are driven primarily by the wind. The trade winds, which blow from east to west in the tropics, push the surface water westward across the ocean basins. When this westward moving water encounters a continent, it has nowhere to go but north or south, forming the great boundary currents that run along the western edges of the ocean basins. The Gulf Stream in the North Atlantic, the Kuroshio Current in the North Pacific, the Brazil Current in the South Atlantic. These western boundary currents are fast, narrow, warm, and deep, carrying enormous volumes of warm tropical water toward the poles. The Gulf Stream is perhaps the most famous of these currents, a river of warm water, roughly 80 kilometers wide and 800 meters deep, flowing northward along the eastern coast of North America at speeds of up to 2.5 meters per second. It carries more water than all the world's rivers combined, more water than the Amazon and the Congo and the Nile and the Yangtze together. As it flows northward, it releases its heat to the atmosphere, warming the climate of Western Europe by several degrees, enough to make London noticeably warmer than its latitude would suggest, enough to make agriculture viable in regions that would otherwise be too cold for it. When the Gulf Stream and its extension, the North Atlantic Current, reach the high latitudes of the North Atlantic, the water has lost much of its heat to the atmosphere. It is now cold, and it is also dense because of its high salinity. The evaporation that took place in the tropical regions where the current originated left behind a higher concentration of salt than the surrounding ocean. Cold, salty water is dense, and dense water sinks. In the North Atlantic, particularly in the regions around Iceland and Greenland, this sinking produces one of the most powerful flows in the ocean, the downward plunge of dense water into the deep ocean, beginning the deep circulation that carries this water southward through the deep Atlantic, around Antarctica, and gradually northward into the Indian and Pacific Oceans. This deep circulation, sometimes called the thermohaline circulation or the global ocean conveyor belt, is one of the most important components of Earth's climate system. It distributes heat from the tropics toward the poles, distributes nutrients from the deep ocean to the surface where they can fuel biological productivity, and regulates the amount of carbon dioxide dissolved in the ocean and exchanged with the atmosphere. The entire circuit takes roughly 1,000 years. Water that sinks in the North Atlantic today will not return to the surface until the 30th century. The Coriolis effect, the deflection of moving objects caused by the rotation of the Earth, shapes the ocean currents in fundamental ways. In the Northern Hemisphere, moving water is deflected to the right, in the Southern Hemisphere, to the left. This deflection causes the great circular current systems, the gyres, that dominate each ocean basin. The North Atlantic Gyre, the North Pacific Gyre, the South Atlantic Gyre, the South Pacific Gyre, the Indian Ocean Gyre. Each of these is a vast circular flow of surface water, driven by the wind and shaped by the Coriolis effect, cycling the water of its ocean basin in a slow clockwise or counterclockwise rotation. At the centers of the subtropical gyres, where the circular currents converge, the water is pushed downward, and the surface is unusually calm, warm, and low in nutrients. These are the ocean deserts, blue, clear, beautiful, and relatively poor in life compared to the productive upwelling zones along the coasts. The Sargasso Sea, in the center of the North Atlantic Gyre, is the only sea in the world defined entirely by ocean currents rather than land boundaries. It is named for the floating sargassum seaweed that accumulates there, carried by the currents converging on the center of the gyre, and it is home to a unique community of organisms adapted to life in and among the floating weed. The ocean currents carry not only water, but also the organisms that live in it and the debris that floats on its surface. The great ocean garbage patches, accumulations of plastic debris that have concentrated in the centers of the subtropical gyres, are a consequence of the same physics that makes the Sargasso Sea a unique habitat. Plastic that enters the ocean from rivers and coastlines is carried by the surface currents toward the gyres, where it accumulates in enormous, diffuse patches of micro and macroplastic that slowly degrade into smaller and smaller particles, but never fully disappear. The currents also carry heat and cold in ways that have shaped the history of exploration. The cold Humboldt Current, flowing northward along the western coast of South America, is one of the most productive fishing grounds in the world. Its cold, nutrient-rich water supports enormous populations of anchovies, which in turn support seabirds and marine mammals in extraordinary abundance. The same cold current also creates the Atacama Desert, one of the driest places on Earth, by cooling the air that moves from the sea over the continent and preventing it from rising and forming rain. The currents move slowly, but with enormous power. They have been flowing for millions of years, following patterns established by the positions of the continents and the rotation of the Earth and the prevailing winds. They will continue to flow for millions of years to come, carrying their heat and their cold and their nutrients and their living cargo around the planet in the great, slow, patient circulation that is the ocean's contribution to the stability of the world. Imagine being a drop of water in the Gulf Stream, warm and swift and northward moving, carried on the surface of the Atlantic in a river within a river, the coast of America a distant shadow to the west. The water around you is the most intensely blue that water gets. The sun is warm, and you are moving slowly and irresistibly toward the cold north, where you will sink and begin the 1,000-year journey through the deep. Chapter 8. Sea creatures of the night, bioluminescence, and the dark hours. As night falls over the ocean, something extraordinary happens. The surface of the sea, which in daylight is lit by the sun and visible for miles, becomes dark. And in that darkness, the ocean begins to glow. Not everywhere, and not all the time, but often enough and brightly enough that the phenomenon has been observed and marveled at by sailors and naturalists and poets for as long as human beings have been on the ocean at night. Bioluminescence, the production of light by living organisms through chemical reactions, is one of the most widespread phenomena in the ocean. It has evolved independently dozens of times in marine life, from bacteria to jellyfish to fish, and it takes forms of extraordinary variety. Some organisms produce a constant, steady glow. Others flash briefly in response to disturbance. Some can modulate the intensity and color of their light. And some, particularly the anglerfish and their kin, use bioluminescence as a lure, dangling a glowing organ in front of their mouths to attract prey in the darkness. The most immediately visible bioluminescence is that of the dinoflagellates, microscopic, single-celled organisms that float in enormous numbers near the surface of warm coastal waters. When disturbed by movement, by a wave breaking, by a fish swimming past, by the bow of a ship cutting through the water, they flash briefly with a cold, blue-green light. A beach at night, with small waves breaking on the shore, can look as if it is scattered with blue fire. A ship moving through a bioluminescent bay leaves a wake of light that fades slowly behind it. Swimming through bioluminescent water, with every movement of the arms trailing light, and every kick of the feet sending sparks upward through the water, is an experience that those who have had it describe as one of the most magical of their lives. Bioluminescent bays, places where dinoflagellates are particularly abundant, are found in various parts of the tropics and subtropics. Puerto Rico has several famous examples. Mosquito Bay on the island of Vieques is considered one of the brightest bioluminescent bays in the world, its waters so dense with dinoflagellates that the glow is visible from the air on dark nights. Jamaica has a bioluminescent lagoon. The Maldives in the Indian Ocean has beaches that light up blue with each breaking wave. In the deep ocean, bioluminescence is even more prevalent. Studies of deep-sea organisms suggest that more than 90% of deep-sea animals are bioluminescent, a proportion so high that the deep ocean, which we think of as being in absolute darkness, is actually filled with light, cold, blue, brief, produced by organisms rather than by the sun, but light nonetheless. The deep ocean is not dark in the way that a sealed room is dark. It is dark in the way that a star field is dark. The background is black, but it is punctuated by light, and in aggregate the light is significant. The function of bioluminescence varies by organism. In the darkness of the deep ocean, where there are no visual landmarks and no physical structures to orient by, bioluminescence serves as a form of communication, a way of signaling to potential mates, warning off predators, or luring prey. Some deep-sea fish have bioluminescent organs arranged in specific patterns on their bodies that are species-specific, a living name tag, readable only to members of the same species at close range. Others have photophores, light-producing organs, arranged on their undersides to produce a faint glow that matches the ambient light from above, making them invisible to predators looking upward from the dark below. A form of camouflage called counter-illumination. The chemistry of bioluminescence is elegant. Most bioluminescent organisms use a compound called luciferin, which reacts with oxygen in a chemical reaction catalyzed by an enzyme called luciferase, producing light without producing significant heat. The light produced is extraordinarily efficient. Virtually all of the energy of the chemical reaction is converted to light, with almost no waste heat. By comparison, an incandescent light bulb converts only about 10% of its energy to visible light, with the rest lost as heat. The bioluminescent organism is, in this sense, a more efficient light source than anything human engineers had produced until the development of LEDs. The discovery and development of bioluminescent chemistry has had enormous consequences for biological research. Genes for luciferase, the enzyme that catalyzes the light-producing reaction, have been widely used as reporter genes in molecular biology, allowing researchers to track the expression of other genes by attaching luciferase to them. Wherever the gene is expressed, the cell glows. Green fluorescent protein, originally discovered in the bioluminescent jellyfish Equoria victoria, has been even more widely used as a biological marker. The scientists who first isolated and characterized GFP, Osamu Shimomura, Martin Chalfie, and Roger Tsien, were awarded the Nobel Prize in Chemistry in 2008 for a discovery that grew directly from the study of an ocean animal's glow. Tonight, somewhere in the ocean, organisms are making their own light. In the bioluminescent bays of the tropics, the dinoflagellates are flashing blue with each wave. In the deep Atlantic, anglerfish are dangling their lures in the darkness. In the Pacific, lanternfish are rising from the deep in their nightly migration, their bodies marked with rows of glowing photophores. In the Southern Ocean, bioluminescent krill are flashing as they swarm in their billions. The ocean is full of cold fire, in colors that range from blue-green to orange-red, produced by chemistry rather than by combustion. Beautiful in the way that the purely functional can sometimes be when it is also perfectly adapted. Let the glow of the ocean's bioluminescence be the last image you hold tonight. Cold blue light in the dark water, a brief flash, and then darkness, and then another flash somewhere else. Not threatening, not alarming. Simply the ocean expressing what it has always known. That darkness is not the absence of beauty. That light can be made from within. Chapter 9. The Ocean and Human Civilization. A story of dependence and wonder. Human civilization has always lived at the edge of the ocean. The earliest settlements that became cities were nearly all coastal or riverine, places where water provided food and transportation and a degree of natural defense. The great civilizations of antiquity, Egypt, Mesopotamia, the Indus Valley, the Minoan world, ancient China, were all organized around water, and many of them had complex relationships with the sea that shaped their culture and their economy and their mythology. The Polynesians are perhaps the most ocean-centered of all ancient cultures. Setting out from Southeast Asia or Taiwan in outrigger canoes more than 3,000 years ago, they navigated across the vast Pacific, the largest ocean on Earth, covering more of the planet's surface than all the land combined, using techniques of celestial navigation, wave pattern reading, and bird observation that allowed them to find tiny islands in an enormous ocean with a reliability that modern GPS users find astonishing. They colonized Hawaii, Easter Island, New Zealand, and hundreds of other Pacific islands, creating a maritime culture of extraordinary reach and sophistication. Polynesian navigators learned to read the ocean the way a scholar reads a text, recognizing the patterns of swell and wave that indicated the presence of a nearby island, even when the island itself was below the horizon. Different islands produced different perturbations in the ocean swell, and experienced navigators could feel these perturbations through the hull of their canoe and use them for orientation. They tracked the stars and the sun and the moon, memorized the rising and setting points of specific stars for specific destinations, and used the flight patterns of birds, which tend to fly toward land in the evening and away from land in the morning, as additional navigational information. The Vikings, who expanded dramatically across the North Atlantic between roughly 800 and 1100 CE, were the ocean navigators of the northern world, sailing in their remarkable longships from Scandinavia to Iceland, from Iceland to Greenland, from Greenland to North America, nearly 500 years before Columbus. Their ships were technological masterpieces, shallow drafted enough to navigate rivers and beaches as well as the open ocean, flexible enough to flex with the waves rather than fighting them, and fast enough to cover enormous distances in a matter of days. The Vikings navigated by sun and stars, and, according to some sources, by a device called a solar stone, possibly a crystal of Iceland spar, a mineral that polarizes light and can reveal the position of the sun even through cloud cover. The great age of European ocean exploration, the 15th and 16th centuries, transformed the human relationship with the ocean. Portuguese navigators working their way down the coast of Africa, learning the patterns of wind and current that governed Atlantic sailing, eventually rounded the Cape of Good Hope and reached the Indian Ocean. Columbus crossed the Atlantic. Magellan's expedition circumnavigated the globe. Within a few decades, human beings had sailed every ocean on Earth and established the broad outlines of the world's geography. The ocean ceased to be the edge of the known world and became the highway connecting it. This transformation was not without its costs. The same ocean routes that connected Europe to the Americas and to Asia also became the routes of the Atlantic slave trade, one of the most massive and most brutal forced migrations in human history, in which an estimated 12 million Africans were transported across the Atlantic in conditions of horrifying cruelty, their lives and deaths and suffering woven into the history of the ocean alongside the stories of explorers and merchants and fishermen. The ocean does not distinguish between its uses. It carries what it is given to carry. The ocean has been a source of food for human beings for as long as our species has existed, perhaps for longer, since the coastal foraging of shellfish and fish may have been important to early human populations in Africa before the emergence of modern Homo sapiens. Fish and other marine organisms feed more than 3 billion people today, providing a significant portion of the animal protein consumed by the human species. The fishing industry, artisanal and industrial, from tiny wooden boats off the coasts of developing countries to vast factory ships that process their catch at sea, is one of the largest food production systems in the world. The ocean also shapes the climate and the weather that determines the productivity of all agriculture. The El Niño and La Niña cycles, periodic shifts in the temperature of the tropical Pacific, alter rainfall patterns across the entire tropics and subtropics, producing droughts in some regions and floods in others with effects that cascade through food systems worldwide. The ocean's absorption of heat from the atmosphere helps to moderate the pace of climate change. The ocean's production of water vapor drives the rainfall that fills rivers and aquifers and irrigates crops. The ocean is not merely the place where fish live. It is the engine of the climate system that makes all terrestrial life possible. Human beings have always been drawn to the ocean, not just for food or transportation or commerce, but for something harder to name. For the scale of it, perhaps. For the reminder that the world is larger than any human agenda. For the particular quality of peace that comes from standing at the edge of something vast and deep and indifferent, where the ordinary preoccupations of a human life become very small and very quiet. The ocean has been the destination of pilgrims and poets and philosophers and the simply exhausted, for as long as there have been human beings to stand at its edge and let the sound of the waves carry something away. The sound of the waves. Let it carry something away tonight. Let whatever you are holding loosen its grip in the presence of something so much larger. The ocean does not need you to be anything other than what you are. It does not care about your worries or your failures or your plans for tomorrow. It simply moves as it has always moved, as it will always move, indifferent and magnificent and alive. Human beings have given the ocean many names. Mare Nostrum, our sea. The Romans called the Mediterranean, with a proprietary affection that is entirely understandable. The ancients called the Atlantic the Sea of Darkness, and the Pacific, so named by Magellan, who crossed it in an unusually calm season, means simply the peaceful sea. The Indian Ocean, the Southern Ocean, the Arctic Ocean. Each name carries the fingerprints of the culture that named it. the particular angle from which that culture encountered the water. But the ocean has no name of its own. It is one thing, one continuous body of salt water, connecting all the coasts of all the continents. And no single name can encompass it. What the ocean gives to human beings who approach it honestly, not to exploit it or to conquer it, but simply to be near it and to pay attention, is a particular kind of perspective. The perspective of scale. The recognition that human lives, for all their intensity and their drama and their importance to the people living them, are occurring within something vastly larger than any single life can comprehend. The ocean has been receiving the rivers of every continent for 4 billion years. It has absorbed the carbon dioxide of ancient volcanic eruptions and the ash of asteroid impacts and the blood of 10,000 years of coastal warfare and the plastic of a single century of industrial civilization. And it continues, it absorbs, it transforms, it distributes, it persists. That persistence is not indifference in the callous sense. It is indifference in the sense of equanimity, the equanimity of something too large and too old to be destabilized by any single event, however significant it seems to those experiencing it. The ocean has seen worse than what we are doing to it. It has seen mass extinctions that killed 96% of marine life. It survived. Something survived. And from those survivors, over millions of years, the extraordinary diversity of today's ocean was rebuilt. Not the same as before. Different, but alive and rich, and in its own way, as beautiful as what came before. The sound of the waves. Let it carry something away tonight. Let whatever you are holding loosen its grip in the presence of something so much larger. The ocean does not need you to be anything other than what you are. It does not care about your worries or your failures or your plans for tomorrow. It simply moves, as it has always moved, as it will always move, indifferent and magnificent and alive. Chapter 10. The Arctic and Antarctic Oceans. The world at the poles. At the top and bottom of the world, the ocean behaves differently. The polar oceans are cold beyond easy imagination, covered for much of the year with sea ice, dark for months at a time, and yet full of life, of extraordinary diversity and abundance. They are also among the most important parts of the global ocean system, the engines that drive the deep ocean circulation, the breeding grounds of species that feed the world, and the places most directly affected by the warming of the planet. The Arctic Ocean, at the top of the world, is the smallest of the world's oceans, roughly the size of Russia, and the shallowest. It is surrounded by land. The northern coasts of North America, Europe, and Asia form a nearly complete ring around it, leaving only the relatively narrow openings between Greenland and Norway and between the Bering Strait as connections to the larger oceans. For most of its recorded history, the central Arctic Ocean has been covered by sea ice year-round, a shifting, grinding, pressure-ridged sheet of ice, typically 2 to 3 meters thick, that has been the defining feature of the Arctic environment for millions of years. Under the sea ice, the Arctic Ocean is not lifeless. The underside of the ice is colonized by algae, sea ice algae, that photosynthesize using the light that filters through the ice above, producing organic matter that feeds copepods and amphipods and other small crustaceans. These in turn feed the fish, Arctic cod for example, that are the primary food source for the seals and the narwhals and the beluga whales that live in the Arctic. The polar bear, top predator of the Arctic ecosystem, depends ultimately on this chain of energy that begins with the microscopic algae on the underside of the sea ice. The narwhal is one of the most extraordinary animals on Earth. A medium-sized toothed whale, the narwhal lives year-round in the Arctic, diving to depths of more than 1,000 meters to feed on halibut and cod and squid on the seafloor. The males bear a single spiraling tusk that can reach 3 meters in length, a modified tooth, the only known example of a straight tusk in any living animal. The function of the tusk is still debated. It may be a sensory organ. It may be a weapon in competition between males. It may have a role in mating display. Medieval Europeans who encountered narwhal tusks brought back by Arctic traders believed them to be the horns of unicorns, and they were sold as such at enormous prices, believed to have magical and medical properties. The Antarctic, at the bottom of the world, is different from the Arctic in a fundamental way. Where the Arctic is an ocean surrounded by land, Antarctica is a continent surrounded by ocean. The Southern Ocean, which encircles Antarctica and connects the Atlantic, Pacific, and Indian Oceans, is the most turbulent ocean on Earth. There are no land barriers to interrupt the westerly winds that blow continuously around the Antarctic continent, and those winds drive the most powerful ocean current on Earth, the Antarctic Circumpolar Current, which carries more water than all the world's rivers combined. The Southern Ocean is extraordinarily productive. The upwelling of cold, nutrient-rich water from the deep ocean fertilizes enormous blooms of phytoplankton that form the base of an ecosystem of extraordinary richness. Antarctic krill, small crustaceans roughly 5 centimeters long, are the keystone species of the Southern Ocean, occurring in swarms so dense that they can be detected from space and sustaining virtually all the large animals of the Antarctic: the penguins, the seals, the whales, the seabirds. A single blue whale can eat 40 million krill per day. The biomass of Antarctic krill is estimated to exceed the total biomass of all human beings on Earth. Penguins are the most charismatic residents of the Antarctic ecosystem. Emperor penguins, the largest of the penguin species, breed in midwinter on the sea ice, in temperatures that can reach -60 degrees Celsius with wind chill. The males incubate the eggs, while the females are at sea feeding, huddling together in enormous groups of thousands of birds, shuffling slowly in a continuous movement that cycles each bird from the exposed outside of the huddle to the warm center and back, sharing the burden of the extreme cold collectively. The chicks that hatch in winter must grow quickly enough to be ready for the sea when the ice breaks up in spring. The polar oceans are changing faster than any other ocean on Earth. The Arctic sea ice is declining dramatically. The area covered by summer sea ice has decreased by roughly 40% since satellite measurements began in the late 1970s, and the ice that remains is thinner and younger than the old multi-year ice that previously dominated. The consequences for the Arctic ecosystem, for the ice algae and the copepods, and the cod and the seals and the polar bears, are profound and cascading. The ocean that is emerging from beneath the retreating ice is a warmer, less ice-covered, more navigable ocean that is simultaneously an opportunity for some human interests and an ecological crisis for the species that evolved in the cold. The Antarctic is changing too, though more slowly. The ice sheets of West Antarctica are losing mass. The ocean around Antarctica is warming. The chemistry of the Southern Ocean is changing as it absorbs carbon dioxide from the atmosphere, becoming more acidic in ways that threaten the ability of krill to form their shells and the ability of other organisms to function normally. The great productivity of the Southern Ocean, which feeds the whales and the penguins, and ultimately the entire Antarctic ecosystem, depends on conditions that are shifting beneath it. And yet the polar oceans retain an extraordinary power. They are still the most productive marine ecosystems on Earth, still home to animals of breathtaking size and abundance, still the engines of the deep ocean circulation that distributes heat and nutrients around the planet. The challenge is not whether the polar oceans will survive. They will, in some form, for as long as the Earth has its current orbit and its current axis tilt. The challenge is whether they will retain enough of their current character to continue supporting the extraordinary diversity of life that has evolved in them over millions of years. Let the image of the polar ocean settle into you. The white and blue of ice, the black water between the ice floes, the extraordinary cold, the penguins on their rookeries, the narwhals beneath the surface, the krill in their billions filtering the plankton from the water. It is very cold there. You are very warm here. The contrast is comfortable. Let the cold of the poles be a reminder of how much warmth you have here, in this bed, in this room, on this particular night. Chapter 11. The Ocean's Future. What comes next? The ocean is not static. It has never been static. Over the 4 billion years of its existence, it has been warmer and colder, higher and lower, more acid and more alkaline, more oxic and more anoxic, populated by wildly different communities of organisms at different times. The changes happening in the ocean today are, in geological terms, very rapid, faster than most of the changes recorded in the geological record. But they are not the first time the ocean has changed, and they will not be the last. The primary driver of current ocean change is the warming of the planet caused by the increase in greenhouse gases in the atmosphere. Primarily carbon dioxide from the burning of fossil fuels, but also methane from agriculture and land use change and various other gases. The ocean absorbs roughly 90% of the excess heat that this enhanced greenhouse effect traps in the Earth system, and it absorbs roughly a quarter of all the carbon dioxide that is released. These absorptions moderate the rate of surface air warming and atmospheric carbon dioxide accumulation, but they come with consequences for the ocean itself. The warming of the ocean's surface waters is already causing visible changes. Coral bleaching events, which occur when ocean temperatures rise above the threshold that corals can tolerate, have become more frequent and more severe. The Great Barrier Reef has experienced multiple mass bleaching events in recent decades, and the proportion of the reef that has been severely damaged is increasing. The geographic ranges of many marine species are shifting toward the poles, following the cooler water temperatures they are adapted to. New species assemblages are forming in regions that were previously too cold for them. The timing of seasonal events, the bloom of phytoplankton, the migrations of fish, the spawning of corals, is shifting in ways that can disrupt the synchronization between species that have evolved together. Ocean acidification, the decrease in ocean pH caused by the absorption of carbon dioxide, is a more invisible but potentially equally serious change. The ocean has become approximately 30% more acidic since the Industrial Revolution began, measured in terms of hydrogen ion concentration. This acidification affects the ability of many marine organisms to build their calcium carbonate shells and skeletons. The shells of oysters, the skeletons of corals, the shells of the tiny pteropods that are a crucial component of the ocean food web. In the Southern Ocean, where the water is naturally colder and therefore absorbs more carbon dioxide, pteropod shells are already showing signs of dissolution in some areas. The expansion of ocean dead zones, areas of low oxygen, caused by the decomposition of excessive organic matter produced by nutrient pollution, is another significant change. Coastal waters receiving large inputs of agricultural fertilizers experience blooms of algae that, when they decompose, consume the oxygen in the water and create hypoxic conditions that fish and other mobile animals flee, and that sessile organisms, clams, worms, corals, cannot escape. The number and size of dead zones in coastal waters has been increasing since the 1960s. And yet the ocean also has enormous capacity for recovery. The marine protected areas that have been established in various parts of the world have demonstrated that when fishing pressure is removed, fish populations can recover relatively quickly, on timescales of years to decades. Areas that were previously depleted have, in some cases, returned to something approaching their pre-exploitation diversity and abundance within a human lifetime. The ocean is damaged, but it is not dead, and it retains the capacity to heal if given the conditions to do so. The future of the ocean is not determined. It depends on choices that human beings are making now and will make in the coming decades. About energy systems, about fishing's practices, about the management of coastal pollution, about the protection of critical habitats. These are not easy choices, and they involve genuine trade-offs between competing human interests. But the basic biology of the ocean suggests that recovery is possible, that the diversity and the productivity and the beauty of the ocean can be maintained and in some cases restored if the conditions for recovery are provided. The ocean will outlast us in any case. Long after human civilization has run its course, whatever that course turns out to be, the ocean will still be here, doing what it has always done. Absorbing sunlight, cycling nutrients, supporting life, exchanging heat with the atmosphere, eroding the coasts and building new sediments, and slowly, over geological time, reshaping the continents themselves. The ocean is on a time scale that makes human history look like a single day in a very long year. And in that perspective, even the significant changes happening now are temporary. A brief perturbation in a 4 billion-year story that has always found its way back to something like equilibrium. That perspective is not an excuse for inaction. It is a source of equanimity. The equanimity that comes from knowing that the thing you care about is larger than any single threat to it, older than any challenge it has faced, and more resilient than any damage that has been done. The ocean will be here. The question is what form it will be in, and how much of its extraordinary diversity and beauty will be present when the human chapter of its history is over. Rest in that equanimity tonight. The ocean is moving as it always moves. The tide is doing what tides have always done, drawn by the gravity of the moon. The currents are flowing, the plankton are photosynthesizing, the whales are singing in the deep water. The world is very large, and the ocean is most of it, and it has been here for a very long time, and it will be here when we are gone, changed and perhaps diminished, but still itself. Still the ocean, still alive, still doing its patient and essential work. Chapter 12. The Sound of the Ocean. A meditation. In the last chapter of tonight's journey, we are not going to go anywhere. We are going to stay exactly where we are, wherever that is, in whatever warm and comfortable place has held you through this long, slow story. And we are going to simply listen. Imagine the sound of the ocean, not the roaring surf of a storm, not the crashing of waves on rocks, but the gentle, rhythmic sound of the ocean on a calm day, when small waves are rolling onto a sandy beach with a soft, repetitive sound that is one of the most universally soothing sounds human beings know. A sound that says, "The water is here. The water has always been here. The water will be here tomorrow." The sound of the ocean on a beach is a rhythm, not perfectly regular, because the ocean is not perfectly regular, but close enough to regular that the brain can relax into it, can let go of the vigilance that it maintains when sounds are unpredictable and potentially threatening, and simply receive the repetition as a kind of comfort. This is why recordings of ocean sounds are used in sleep aids and meditation apps and hospital rooms and anxiety treatment programs. The brain recognizes the ocean as something ancient and familiar, something that was the soundtrack of our earliest evolutionary history, when our ancestors lived at the edge of the sea, and the sound of waves was the constant background of existence. The sound of waves has been described by neuroscientists as a form of pink noise, a particular distribution of sound frequencies that the brain finds naturally pleasant and conducive to relaxation. Unlike white noise, which has equal energy at all frequencies and can feel harsh, pink noise has more energy at lower frequencies, giving it a warm, full quality that feels comfortable. The ocean is not perfectly pink noise. It varies too much for that. But its average spectral character is close enough that the brain responds to it with the same relaxation response. Beyond the sound of waves, the ocean has a deeper sound that most of us never hear. The sound of the ocean's own life. The clicks and squeaks and songs of marine mammals. The snapping of shrimp colonies, which produce a continuous crackling sound audible for hundreds of meters. The low-frequency hum of blue whale vocalizations, audible with the right equipment across entire ocean basins, the chorus of spawning fish, the sound of rain on the ocean surface, the deep, slow groaning of the sea ice as it moves. And beneath all of these biological and meteorological sounds, the ocean has its own geological soundtrack, the distant rumble of underwater earthquakes, the low hum of deep-sea volcanic activity, the grinding of tectonic plates. The earth is not silent. It makes sounds that travel through rock and water for thousands of miles, sounds that most of us will never hear, but that are present nonetheless in the deep acoustic world of the ocean. Scientists who study the soundscape of the ocean, bioacousticians and oceanographers, describe the ocean as getting quieter in some respects and louder in others as human activity changes its character. Ship traffic has increased the low-frequency noise in the ocean significantly, affecting the ability of whales to communicate over long distances. Blue whale songs, which once traveled entire ocean basins, are now masked by the noise of shipping in heavily trafficked areas. But in the areas where marine protected areas have reduced fishing pressure, the biological sounds of the ocean, the fish choruses, the marine mammal vocalizations, the crustacean snapping, have increased as populations recover. The ocean has a voice, and when it is healthy, that voice is rich and complex and full. Lie very still and let the imagined sound of the ocean fill your mind. The rhythm of the waves on the beach, slow, regular, warm. The sound rising and falling with each wave, each one slightly different from the last, but all of them part of the same continuous pattern. Each wave a sentence in a language the ocean has been speaking for 4 billion years. A language that your body understands even if your mind does not. A language that says, rest, rest, rest. The water is warm. The night is quiet. The ocean is moving as it always moves, its billions of tons of water shifting in the dark under the influence of the moon and the wind and the deep currents that have been circulating since long before there were human ears to hear them. You are very small in relation to this, and the smallness is comfortable. You do not need to be large tonight. You do not need to be anything other than what you are, a small, warm creature, held by gravity and by atmosphere and by the long accumulated safety of a world that has spent 4 billion years making itself suitable for life. The tide is coming in. Somewhere, very far from here, a wave is being born, a disturbance on the surface of the water, set in motion by the wind, beginning its long journey across the open ocean. It will travel for days, for hundreds or thousands of miles, its energy declining slowly until it reaches a shore and breaks, its final gesture a soft rush of water up a sandy beach, and then a gentle retreat, leaving behind a line of sea foam and small shells and the faint smell of salt. That wave was born in a storm you will never know about, in a part of the ocean you will probably never visit, and it has traveled farther than most people travel in a lifetime. And it ends in this: a quiet breaking, a rush of water, a retreat, and the next one already coming. The ocean is full of these arrivals, these endings, these beginnings. Every shore in the world is receiving them, right now, in every language of wave and surf and the particular sound of water on whatever particular stone or sand or coral that shore is made of. You are part of this. The water in your body came from the ocean, fell as rain, ran in rivers, was drunk and metabolized and eventually returned to the sea. The oxygen in your lungs came from the phytoplankton of the surface ocean, produced by the same chemistry that the cyanobacteria used 3 billion years ago to transform the atmosphere. The salt in your blood, in the concentration that has been constant in the blood of vertebrates for hundreds of millions of years, is the salinity of the ancient ocean from which our ancestors first emerged onto land. You carry the ocean inside you, as you carry the stars in the iron of your blood and the calcium of your bones. That is enough for tonight. The ocean has told its story. The tide is in. And you are part of the story. You have always been part of the story. The ocean does not end at the shore. It continues in a different form in every living thing that ever came out of it and found a way to carry it forward. In you, tonight, breathing slowly in the dark, the ocean is resting, and so tonight's journey comes gently to its end. We have traveled from the sunlit surface to the abyssal dark, from the coral reefs of the tropics to the ice-covered polar oceans, from the 4 billion-year history of life in the sea to the sound of a single wave breaking on a sandy beach. We have been in the company of blue whales and narwhals and anglerfish and sea otters and emperor penguins and bioluminescent creatures, making their own light in the permanent dark. We have moved through the ocean the way the ocean moves, slowly, with weight, without urgency. The ocean is the oldest home our species has, not our current home. We are land animals now and have been for a very long time. But our deepest, oldest, most cellular home, the environment in which life arose and in which it lived for the first 3.5 billion years of its existence. We carry it with us in the salt of our blood and the rhythm of our breathing and the inexplicable comfort we feel when we are close to the water. The ocean is not external to us. It is inside us, in the most literal biochemical sense. The ocean is out there tonight, doing what it always does. The tides are moving, the currents are flowing, the phytoplankton are photosynthesizing wherever there is enough light, and in the darkness of the deep, the bioluminescent creatures are making their own. The whales are singing in frequencies too low for human ears to hear unaided, their songs traveling across hundreds of miles of open water to other whales they may never physically meet. The sea ice at the poles is doing what sea ice does, forming and melting in the rhythm of the seasons. And you are here, warm and still and breathing, at the end of a long day, in a comfortable place, with the story of the ocean settling into you, the way the ocean settles into everything it touches, slowly, persistently, leaving a faint trace of salt behind. This has been nap-time knowledge. Let your body release the last of the day's tension. Let your breathing slow to its nighttime rhythm, long and low and easy. Let the images from tonight drift through your mind without effort or direction. The blue of the open ocean, the cathedral light of the kelp forest, the darkness of the abyss, the cold fire of bioluminescence, the sound of the tide. The ocean is patient. It will be here in the morning. It will be here long after morning. It will be here long after all of us. And in that permanence, in the knowledge that something so beautiful and so vast and so alive is simply here, doing its work, regardless of what any single day brings, there is a comfort that is perhaps the deepest form of rest. The tide is in. The night is quiet. The ocean is breathing. Good night.